All right, everybody, we're about ready to begin this ceremony here. No, it's not a ceremony, it's a presentation. So my name is Gary Klass. I work for Teradata. I'm the banking financial services guy for Teradata. And I'm just going to kind of tee things up. And because Karthik is going to advance the slides, he has to come up as well. Karthik Guruswamy, I'm sorry. A little bit about if you're not familiar with Teradata. Teradata is a relational database engine that runs on-premise or all the major cloud service providers, most of the biggest banks in the world, telcos, government agencies, most of the organizations in the world that have a lot of very complex data are Teradata customers, literally in almost every continent, not Antarctica, but pretty much all over the world. Teradata also has embedded analytics that we call ClearScape that has a lot of statistical machine learning functions that allows you to do those things in database. And recently we've been very focused on extending into the world of AI. So I'm going to preface this because I'm really kind of on the business side, having worked for 35 years in banking, and you'll figure out which bank I work for in a little bit, is that we have this belief that organizations, that the strongest signal that you can get from the data that you acquire is really what you can get directly from a customer, whether it be an email or a chat session, or most importantly, an inbound phone call. For example, if you're a bank or another company that has lots of clients. So the strongest signal comes directly from the customer, but as I'm sure we're all aware, that historically has been a very difficult thing to do. I did really early days text analysis of emails, and the bank I worked for, I did the first ever speech analytics. So we're going to talk about today about how you can use neural architectures and natural language processing to understand what your customers are trying to tell you so you can do a better job of supporting and servicing them. And a little bit of motivation from a business standpoint. Generally, people want to know, yeah, this is great in theory, what's it like in practice? Well, I can tell you, one of our largest banks in the world that I used to work for, we've been very successful working with them to analyze speech and text to address a lot of business problems. One is what's called email surveillance. Basically, banks have to monitor the inbound communications to make sure that they respond to them and understand what the issues are with customers. Our ability to support that and eliminate a lot of hand coding and evaluation of emails saved the bank $51 million. The one in the middle is the one that's nearest and dearest to my heart, which is customer complaints. I used to focus on this at the bank I worked for before I came to Teradata. Really the challenge there is to understand what is it? What is the root of the complaint? What's the issue? What's the banking task, we call it, that didn't work well? We're able to use the technology of Teradata and what Karthik is going to talk about to have a material impact. We're $64 million. And the third one in our sequence of greatest hits here of business applications and natural language processing, or what is known as employee allegations. This is one that somebody works for the bank said, hey, they asked me to do something I don't think is right, or maybe we shouldn't be promoting this type of investment. So once again, the ability to deploy natural language processing at scale using Teradata, led that bank to save $28 million. So we're not talking about peanuts here. It's real money, and the key thing for Teradata is really the scale of the analytic complexity that we can support. And with that, I'm going to turn it over to my esteemed colleague and my favorite data scientist of all time, Karthik Guruswamy. Karthik?
Thanks, Gary. Hey, everybody.
Try talking to this.
Oh, sorry. Yeah, so as Gary was saying, I'm a data scientist at heart. So I've been working with NLP for the longest time. I don't know if anyone here will remember say maximum entropy Markov models. Any? Okay, yeah, so it's that far. Oh, you do know, okay. So, so I've been working for a very long time on this, playing with all the, Penimum, all the tree, grammar type of thing. And then I did a lot of text analytics with Gary a long time ago, trying to understand the email complaints surveillance use case. And, that was the best you could have at that time. There was a lot of effort that was put in to do natural language processing, right? And it's obviously an evolution. So basically, we'll be talking about just the differences between the NLP, the natural language, classical NLP, and the modern, you can kind of call it NLU. There is some debate on whether semantic similarity understanding or what? It's like, okay. And then we're talking about vector embedding, sequence generative concepts. You all know this. You've attended so many days of transformer-based talks and LLMs, so I won't go too much into it. Just want to set up the stage for the next ones. We'll talk about language models as the large language models. So the language models are like smaller ones, like 100 megabyte, 200 megabyte. What is that they can do versus big LLMs and what you can get out of it. And all of this is grounded to solving customer use cases, right? So I always pivot everything towards, if you can't solve a customer use case, so what? Right? That's kind of how I think about it. In fact, Teradata thinks about the same thing, right? Because we want to deliver value for the customer, which means that if you build these things, will it solve problems? Will it cut down time, the ROI, right? And then everything becomes suddenly you can connect the dots more meaningfully, right? So some ideas fall apart, some ideas, even though it may not be the bleeding edge, might be extremely useful, and we want to know what those are. And then we'll go through some business use cases, and then yeah, so you can see, like, we'll also do some share some benchmarking on when you run these language models in Teradata Vantage, which is a distributed parallel architecture, right? How does it compare when you're running it on a GPU farm, and what are the trade-offs and how customers are using it? And then we'll go through a couple of more examples on the inputs and outputs on some of the functions that we talked about. We'll give you a little demo in the middle, okay? So as you all know, the classical approach of NLP is just statistical modeling, part of speech rules around n-grams, right? Could be bigrams or trigrams. So this is like the old school way of doing it, right? We extract sentences and we want to lematize it. You all know all the NLTK type stuff. And then you do the TF-IDF, right? All of that. And then you basically have like a sparse matrix, and then you will do some PCA and then try to fit into an XGBoost model. So we have done all of this in the past. The problem comes, some of the problems are either multi-class or highly imbalanced. So let me give you an example, right? So when you get customers complaining about it, some of the complaints may actually lead to regulatory fines that can actually trigger. So it'll be like a needle in a haystack. So if you're going to, let's say, caught like 10 emails in the past, just looking behind, and you can't really build a model on that using this n-grams, because the new complaints that are coming in, right, may not even have the same words. So what are you trying to do? So you're going to get a lot of false positives and negatives. And believe it or not, there's a lot of operational cost when you deal with false positives and negatives in the bank. Sometimes they put like big call centers for people to go through all the false positives and negatives. So it's going to incur a lot of cost. So the model, the more tighter and more accurate it is, everybody wins, right? But this is the best techniques we had that day. And then even searching for things, like when you're looking for certain types of patterns, in the past we used to like regular expressions to find certain types of expressions, English expressions in the text to see if somebody is talking about this topic or whatever. That's a lexical search, right? There's also a little bit n-gram based search. Well, you can create like, inverted indexes and Solr and Elasticsearch, all of them is there, but it's still a needle in a haystack issue. And so the world has moved on since then to more neural models, right? Like the next evolution was word-to-vec and fast-glow, as you all know. Word-to-vec, bag of words, looking around words, like, but it really definitely missed the positioning. And that's when the attention and all you need paper came in, and then you got all the positional encoding and a lot more context when you build the models. So this is all like a little bit classical approach, going from statistical model to a little bit of neural models. But now we are doing it on steroids, right? I mean, literally like GPUs and processing and all of that. So I want to actually spend a couple of minutes. Yeah, I want to walk around. Can you hear me? Oh, I got to turn this on. Yeah, I want to talk about a couple of, I try to put all of this in one slide. It probably took me like a week to get it in, to be honest. Because there is a lot here, and to me, I want to build a model of all models. I want to be able to understand or talk to somebody about, encoder. What is an encoder? What's a decoder? What is generative? Today, right now, everything is generative AI. Right? That's not true. A lot of people don't understand. Like creating a vector embedding is not generative AI. It's the opposite of that, right? So I try to put all of this. So basically, as you know, I'm almost sure everybody here knows what I'm talking about already, but I'll just quickly go through this because some of this is relevant to what we're doing inside Vantage. So generally, we try to put these models in 3 categories: encoder only, decoder only, and encoder decoder type categories. So encoder will be more like BERT and derivatives, right? Like, are you including the modern BERT? I don't know if you're following. Anyone knows modern BERT? Are you reading? Yeah, it's just, BERT's got 512 tokens as context. The modern BERT has got 32K. So it's been retrained by Tom Arsenin from, if you just follow on LinkedIn, you'll see some of that. And then decoder only is all GPT, the llamas, right? So it's all based on GPT decoder models. And then the last one is the encoder decoder, where you train them together, like something like a FLAN T5 or a BART-based model. So let's talk about an encoder model first. In the encoder model case, you have a bunch of text, right? And then you are going to tokenize it, which is like converting the terms to numbers, right, with using a tokenizer.json or a dictionary. And then you're going to run it to the encoder model. This is the inferencing part, not the training part. And then you're going to get a vector embedding, like a fixed length array. So regardless of the type of text, the length of the text, you're always going to get a fixed length vector here, right? This encoder model. And this is obviously trained on, like a BERT derivative, and you have trained on so much of data set and fine-tune. So today is a little bit of an inferencing type talk. Just to let you know, we won't be talking about fine-tuning LLMs or anything. But I can tell you what the inference world looks like. Maybe if something take away from this talk is just like how the inferencing can be used for various different applications, right? So you got the embeddings, vector embedding. So obviously the length of the embedding depends on the encoder model, varies in size, varies in latency. There's a lot of properties to the model when it comes to production application. You really don't want to bring in an encoder model that takes like half a second to create an embedding because it's got 32K dimension. Nobody's going to use it. Rather, you also don't want a very small model, right? That inference is fast, but is missing out on financial data, for instance, like it's, right? So you really want to find the right model fit, if you want, like a golf club fit or a bike fit, right? And obviously that goes through all the evaluation. The second one is the decoder one. This is all like the, that's a generative model, because it's generative model when you generate text, audio, or video. It's not generative when you're generating this. Somehow, like, I'm trying to constantly correct people, and they say loosely use the word Gen AI for everything. Anyway, so this one I would call it as like interpolation on steroids. That's like extrapolation on steroids. You're trying to do like really fancy extrapolation, and this is all based on, BERT is based on it, trying to interpolate things, right? So very different type of model. There's a third type of model, which is the encoder decoder or the sequence-to-sequence model. Has anyone used any sequence-to-sequence model in the past? Like a FLAN T5, for instance? Have you? Okay, which model, may I ask, if I'm not putting you on the spot? I see. Yeah, so this is great. These models, there is a FLAN T5, if you can Google it later on. I mean, no pun, like they're created by Google. So T5 is it's a class of transformer sequence-to-sequence model where you're given some text on the text context, like this, and then it out comes a summarized version of text. It's really good at point tasks. Like it can do like translation, English to French, or French to English, or whatever language it's tuned on. The model is somewhere about 1.5 gigabyte to about 4 gigabyte in size. Takes about a second on a CPU, like a couple of seconds on a CPU if you're using like it also has beam search inside. So you can set the beam search saying that, hey, I want to have 10 beams or 15 beams, and obviously it's going to take it's got length penalty, it's got a couple of hyperparameters, and it doesn't hallucinate. Isn't it wonderful? Why I love banks don't want their models to hallucinate, okay? This is the problem. You don't want anything to be unpredictable. You want it to be predictable, even if it's wrong. You want it to be consistently wrong or consistently right, okay? That is why all the large language models fall out long time. It never gets to production, except for corner cases, except for highly unregulated. Gary, correct me if I'm wrong. So Gary used to work for a bank, so I want to make sure that he keeps me honest. So I'm not hallucinating. So basically, I love this stuff because it doesn't require a whole lot of GPU power to do that. So if you want to summarize text using an LLM, I don't know, but it's a Michelin restaurant. Are you all familiar with the Michelin star restaurant, like the fine dining, right? I'm sure. You don't, in Teradata, we say you don't need a Michelin star chef to do a cheese sandwich. If you're trying to just summarize, do you know the cost of setting it to a large language model to do it? Large language model will do it unbelievably beautiful way, okay? But it'll hallucinate. It can come up with different summaries each time. There is also latency involved and cost for GPU. The sequence-to-sequence models can still run on GPUs, run a lot faster, and it can summarize a whole lot, and it's not going to hallucinate. You can even fine-tune it. If it hallucinates, you can take it back, you can fine-tune it, you can set the seed, and it's going to do, like, you can set the seed on the sequence, always going to give you the same summary. And worst case scenario, the Google Flan T5 model, you can even put a little prompt in the front. It can do about 10 different tasks. You can say, like, answer it technically, : summarize it only with the technical information, : you can point it, it'll do the exact same thing. So it's very repeatable, and we love that stuff. Encoder also doesn't, see, encoder might hallucinate in the sense like it might create the wrong encoding for the task, but it will always give you the same numbers from what I've seen, unless you've seen it differently. So that's why we love the encoder and the encoder decoder. Decoder, Teradata, we use it for we have it externally running on GPU farms. If you're doing a RAG or whatever, it is going to be extremely useful, right? So those are the three things that we want to talk about. And obviously you all know Hugging Face. So all of this is probably like, if you look at text classification, it's probably like a classification head on top of an encoder model. So basically the underlying models remains the same, but you're going to put like a lot of icing in the cake on top, and you get all the other models, right? And even for sequence to sequence, you can also do like automatic speech recognition. It's also like generative. You can have a sequence to sequence model, right? So you can have audio coming in. You're going to have like something like a CTC tokenizer. It's a different type of tokenizer, but you're going to get the text at the end. So there is all the ASR models can be used in this form, right? So it's still generative, but you're going from one modality to the other, audio to text. You can do image to text, you can do text to image. There are a lot of sequence to sequence models in Hugging Face that can do this point task really well, okay? All right, so you all know this. So there are proprietary models. This is for folks who are not from the AI well necessarily, but I just want to quickly show you a couple of things. All the proprietary models are there by the cloud providers. Teradata has strong partnership with all the cloud vendors. And then obviously open source, Hugging Face, there's everything there. So we're going to just focus on the encoder model and the sequence to sequence model. And then have you heard about this? Have you seen, any of you seen this, MTEP? If you're going to choose an embedding model, you can actually go to the massively text embedding benchmark, massive text embedding benchmark. It keeps updating every day. So you're always going to see what's in the leaderboard. You can choose the number of parameters, number of 40 million parameters, and then you can choose the size of the model, right? So you'll have both proprietary and open source models across various different benchmarks. And there's a way to shop around and find the encoder model to see what fits your application, right? Right? You always don't want the biggest and the baddest encoder model. May not be practical to run it. And you also want to have the smaller the model, there's a pretty good likelihood that you can actually run it on a CPUs. You don't even have GPUs. But not on a single instance. I'll show you, like, you probably need to have multiple. So generally, GPUs are about 100 to 200 times faster. The lowest is 75 depending on the model size. So you have that. So there is a way to use it in a way that you are not hogging the GPU farm, and use that for only high value tasks like fine-tuning. Fine-tuning is going to take a lot of time. But for inferencing, using a GPU might be an overkill, especially for these types of use cases that we're going to talk about pretty soon. The other one is, so what we have done in Teradata, let me check the time. Okay, I got to get through fast. So on Teradata, we have a home in huggingface.com/Teradata. So what we have done is we have taken a bunch of models and converted them into Onyx format. Okay, so anyone here knows about Onyx? Are familiar with Onyx? So Onyx is an open source consortium. Teradata is also part of it. So basically, NVIDIA, AMD, Intel, Microsoft, they're all part of it. They have quarterly meetings. So this is an open standard It's basically a standard wherein it's kind of like the Switzerland, or you can say like the neutral ground of a model. So you can bring a PyTorch model or a JAX model and convert to Onyx, and you need an Onyx runtime for inferencing. It's mostly used for inferencing. And the Onyx, the reason why you want to convert to Onyx is because a model in PyTorch, and if you look at the same model convert to Onyx, Onyx will be a lot more faster than running in PyTorch because it's got a graph optimization built in, right? It's a computational graph, right? The PyTorch models, so is Onyx. And depending on the runtime, the operators, so it's very, and also optimized for the hardware you're running on. So it's optimized for CPU, and vendors are trying to optimize it for their own hardware, including NVIDIA. So if you take a model and convert to Onyx and run it on the GPU, the Onyx model will run at least 20 to 30% faster on the GPU than the PyTorch model. So it's mostly for inferencing, right? So it's so you got that. So we have some encoder models and sequence-to-sequence models that Onyx convert to Onyx that we published there. And those are the Onyx model that is going to run inside Teradata, and I'm going to show you how that is, okay? So really quick, we have the large language models mostly. We call it this way for Teradata's sake, like all the decoder models fall here. Anywhere from 4 gigabyte to 700 gigabyte falls here. All the smaller models, we just call it language models. We don't call it small language models because it is like, it's a loose definition, right? The smiling, so as you can see, like what is small? Run on a Raspberry Pi, you call it small? So you say, okay. And so we say anything around 1.5 gigabyte, less than 2 gigabyte, let's call it language model, can run in Teradata. Anything above that, you need a GPU farm, go run it on a GPU. So why is it, how can it even run on Teradata? Teradata doesn't have GPUs inside the platform, but we do have integration with NVIDIA, partnership with NVIDIA to do things outside. That is because Teradata has been around for 40 years. I don't know if you know this. Yeah, so let me tell you, it started as a computation company. They are the first one to say massively parallel processing. They're not saying massively parallel storage. It's massively parallel processing. So they came up with the idea that if you have multiple servers and you can distribute the workloads, their optimizer is built to do MapReduce like queries on SQL queries to distribute the computation across multiple nodes, right? Those days CPUs, they hardly, if you put like a terabyte of data those days, it's huge. That's why the name Teradata came, because we were able, first one to put a terabyte on a database. And the way it works is that you have the CPU parallelism. You can call it cores in a single node, or you can have multiple nodes connected by a high-speed network. And here's the thing. The storage is also connected to these amps. Like if I have 100 units of parallelism, and if I load a table with 100 rows, assuming like a perfect distribution, all these amps will see one row of that data. So when you're doing a group by, or if you're doing like, whatever you want to do, everything happens locally first, like MapReduce, right? But the data never moves across the network unless it really has to. So if you look at a Spark-based architecture, like some of our competitors, there's a lot of data shuffling happens. So what happens is that because we don't move a whole lot of data, thousands of users, concurrent users can run in Teradata because they can, it's highly concurrent system and high performance in benchmarks, right? So it's extremely good at benchmarking SQL queries because it doesn't move the data a whole lot. And it's also called, linearly, it's called like a shared nothing system, which means every time I'm doing something, I'm always not talking to the other amp or moving the data around. And it also scales linearly, which means you double the system, you can run the queries 2 times faster, and it's linearly scalable for most part, except for some corner cases. So that's been the legacy of Teradata. I don't want to lecture too much, you all know too much. I just kind of say this. Okay, so what we are doing right now is to bring these Onyx models and running it on the CPUs. So if you have enough parallelism, then what happens is that the Teradata becomes like a powerful GPU. Most of our customers are sitting on 2,000 or 4,000 type units of parallelism. So they're probably sitting on 10, 20 GPUs. So the data never has to move out of Teradata. We can bring in the sentence transformer, but for one row, it's going to be 100 times slower than a GPU. But if you're having 1,000 level of parallelism, so you're going to be 10 times faster, right? Like an equivalent of 10 GPUs. So that's what we're trying to accomplish here. It's good for batch inferencing, not for real time, right? So for real time, you don't need a GPU. So we're being very realistic here. So we're not giving you anything wrong information. So these are the type of use cases that is in general, with or without Teradata, it's, our customers are using right now. Semantic search is going to be the most popular one. And then you'll see you can look for things like identity theft with debit card. Who's complaining about identity theft with debit card? We want to find out all the crucial problems because there are product managers for debit card, product managers for credit card. So they want to know what's going on with their customers. And then you can do semantic clustering, just like K-means clustering on embeddings and trying to find topics and then trying to explain post hoc. Third one is text summarization. A lot of them get like audio to text transcription from call center. They want to summarize and say what this conversation is about. And you got RAG, you got zero shot. For feature engineering, sometimes they want to combine text and numeric and categorical data, so you can bring in embeddings. Now we are doing entity matching with this embeddings. Anyone know about cross encoders and bi encoders in this class? Yeah, so you can create embeddings for two entities and then you can match. So it can even go across languages when you do. Did you know that you can even do semantic search multilingual? You can ask something in English and you'll find it in Arabic. There's no way you can do it by any other way. Okay, so there's a lot of things that we are coming from customers. And then we are going and checking to see if it works, and it works, and suddenly it's useful. Right, so the key thing is to bring the analytics to the data as opposed to move the data around, because text is pretty heavy. When you move it around, you do the inferencing, you have to book time with the GPU farm. Here, it's running 24/7 along with the SQL queries. And then image OCR, converting invoices to computer vision models. If it's got to be small enough, though, to run like a donut model that's small enough to run Advantage. Q&A, zero-shot classification is very popular. So zero-shot classification, I'm sure if you don't know, it's like just before you classify, you say what the labels you're interested in, and it'll go and classify it based on what you asked, just during runtime. It does not be trained on specific labels. So you can say, hey, I got this text, and I want you to classify into 6 categories: happy, sad, confused, checking, savings, and something else. And it'll go find the one that matches the most and also give you the probabilities on the other ones. So you can pick the best emotion and the best product, and you can just do that on the fly without, and then you got language translation. In California, we have a lot of Spanish-speaking customers. Here, I'm sure you have a lot of French-speaking customers. You want to convert it to English. You got a sequence model for that. And if you want to bring it to English, you can do the other way too. This is a huge one, PII detection, social security numbers. You want to be able to, and also removal. So there are some new PII models on Hugging Face. Just take a look at it. This is another one, repunctuation, grammar, and spelling. Sequence to sequence, classic example, right? So you have the audio to text converter, and it's fully garbled. You want to be able to reconstruct it in a way that's readable, you can do it. Text paraphrasing, so I can go on and on. Yeah, so we talked about this. So as I said, Teradata architecture is parallel. There's some attached disk, but it can run in the cloud on-prem. We have connectors to all kinds of data sources. Today we're bringing data from Hadoop, flows gets hash partitioned into the storage. All the computation done. You can bring your own models like Hugging Face models or PMML and run it in shared nothing mode. And that is the design pattern 1 that we're going to talk about. Design pattern 2 is on the cloud, we have a way to spin up this on-demand cluster. I think Databricks also does that. So you can spin up an even Snowflake, we call it like a sidecar cluster. You can spin up a sidecar with a GPU, and in which case you're moving data from here and do something that doesn't fit here. Let's say you have a 4 gigabyte model that doesn't fit here. Today we are doing that by spinning a sidecar. Snowflake and Databricks also does that, I think. So the third one is we have a partner with NVIDIA and NVIDIA. So you can move data from here, run the embeddings there if you want, and bring the data back. So there's like different design patterns, but the use cases remain the same. Yeah, so this is just like our Teradata Vantage is also a data science and machine learning platform, if you don't know. I'm not trying to sell anything. I just want to share some information here in this conference. Just more like awareness on what we can do. And what customers find the most exciting is bring your own model. We call it BYOM. So a lot of customers are using, because you can bring these models and do, because we can't keep up with the training. So for example, like I used to work for a company called H2O.ai. Are you familiar with, anybody familiar with H2O? They actually like an open source machine learning platform. It got AutoML, so you can build all the AutoML models, run the random forest, all of that, build a stacked ensemble model. And then you can bring it inside Vantage and score it in parallel without moving the data. So, and they're already doing reporting, they're doing all kinds of analytics. Now we are also running these inferencing as well. There's also a feature store for customers. And then there's like all kinds of partners to connect to Teradata. Yeah, so that's kind of the Teradata story there. Okay, I know I've been talking a lot. Any questions before we, anyone has any questions? I think you can put in the chat or something, but we are all here, so I can see all of you. And then I can go to a demo. I'll give you like a couple of minute break.
Come on, somebody's got a question. Come on.
Thank you for the presentation. When you said that sentiment, semantic search in multilingual or multi-language, can you give me some use cases about that and how it could be helped, the application of that?
Yeah, absolutely. So let's say you have you're in a bank, I know, and then there is a call center agent speaking in French, for example, explaining the problem, and two people are talking, and then the data gets converted into, comes into our somewhere. It doesn't have to be Teradata. Let's just talk about the multilingual semantic search. Now, there's a product manager who's looking for complaints like the identity theft in a credit card, right? So if you have a multilingual embedding, and if you're able to do a semantic search, the multilingual model, embedding model, can convert French into embeddings, no? It can convert. But when you search for it, it's going to have the same semantic content of your question, and it actually matches the embedding because they all map to the same space. So there is a way to do it, and we find it more exciting even in entity management. Like you're trying to match a merchant name, and then across comes in the credit card statement. They're trying to match then, or items in the invoices, right? And it's one of our banks is in. We have one of our customers in the Middle East, and they have all of these things in Arabic. And they're trying to match an English categorical like transportation, hospital, like the different expense categories. They're trying to match that with the invoice thing. So on the left side is English, which is standard, like an ISO standard equivalent of taxonomy. And when you're trying to match these things, then it's all in Arabic. So we created the best GT multilingual model just out of Hugging Face. Didn't even fine tune it. Created embeddings, and then we're trying to do a match. And we do this embedding, and we did some cross encoding. And then we did some joint classification of some sort. So, and then we found that the accuracy going from their old way of doing it to the new way shot up 20% higher. So using embeddings for anything can give you the lift, right, in terms of going from a traditional way of doing it. So there's a lot of opportunities. Yeah, as Gary was saying, all the banks use Teradata, almost all the top Fortune banks. So now they don't have to move the data elsewhere or to a GPU farm to do these things. All of this can be done within the platform, right? And you only go to the GPU only when you really need it. So so this is what this talk is all about. How does this work? It's a CPU parallel. It's all about parallel. The parallelism, even GPUs are parallel, right? The GPU, the way it's designed, all the cores are parallel, right, with the interlink connect behind. So this is just using the existing technology to level up the game in doing this. Because it's a regulatory environment, it's very difficult to move data from on-prem to the cloud. The banks only put things on the cloud. It's happening, but it's not fully happening. Still, a lot of data is in on-prem. So how do you bring the AI to the data is kind of what we are trying to do right now. All right, so So let's, I'll show you like how this works, and please stop me anytime. I don't want to bombard you with information, or too much information. So, but I think you'll find this interesting. I'm just going to show you a Jupyter notebook. Let me make it a little bit bigger. Is it better? Can you see it? Okay. So basically how this works in Teradata Vantage, we're going to show you, so basically we pick a model from Hugging Face, like a ByBG model, which is very popular. They get about like 500,000 downloads a month. It's about 130 megabytes in size. The safe tensors are about like the model, the weights, right? So there is a tool, open source tool called Optimum CLI that's built by Hugging Face. You can actually Google the Optimum CLI. It's from Hugging Face. There's some maintainers on it. They have GitHub issues. There's like you can go and, so we keep putting all the tickets there saying, hey, can you support modern BERT, you know, that sort of thing. So there's always people who pick it up real quick. So you can actually, there is a command called export onX. You do have to set the offset to something, because this offset is connected to the runtime version of the inference engine, right? So there are different, onX also releases different onX, different inference runtimes. So whenever you are exporting an onX, you have to make sure that it is backward compatible with the latest one, right? So there's a way to set the version. Teradata uses offset 16. And then you basically like say, hey, convert it to this onX. A directory, put it under onX. 2 years ago, if you go to Hugging Face, pick a model and you look in the folder, you will not see onX. But recently, if you look at a 2-year-old model, you will see an onX directory there, because even Hugging Face is converting models to onX as an alternative for users to use it. So it's not a proprietary Teradata format or anything like that. So you do that, it gets converted, and then you can see there is both token embeddings as well as sentence embeddings. This is the mean pool one, right? So it's done on tokens. And then what you can do is you have a way to, so there is a slight difference between, PyTorch. PyTorch is more static DIMMs. onX is a little bit more dynamic DIMMs, so it's kind of like fun to play with for inference. So you can specify things on the fly, right? So here I'm actually, there is a Python library called onX and onX runtime. Here what we do is that we load the onX that we converted from here, right? And then you can see the graph. It has the sentence embeddings and token embeddings nodes. And then you can, and because it's a CPU, you can set batch size as 1024. You can use go up to 8 maybe batch size if you want to do batching. CPU is just a little thing, right? And so you got to set that up, and then the sequence length is already set. I'm just setting it up explicitly, and this is the output vector size. And then I'm removing the token embeddings of no interest. So I just like drop that node. Again, you don't have to worry about this. You can go to Hugging Face /Teradata, and we already did all of this. I'm just showing you like how the sausage is made. And then you got the graph embeddings. And then whenever you convert to onX, regardless of whether you're using Teradata or not, you have to do a sanity check to make sure that it's working correctly, exactly like the PyTorch model, because you're converted from, right? So what we do is we bring in 2 sentences, and then we tokenize it, and then we are actually converting them into ENC and ENC2, both the embeddings. And then we're doing a cosine similarity of both the embeddings, right? And then you get like 0.91, because both of them are pretty much like saying the same thing. So it's actually, when I say cosine similarity, it's not cosine distance, it's similarity, right? So cosine similarity is 1 minus distance. That's why it's a little bit high value. If it's a cosine distance, it'll be 0. Very less. And then you do the same thing with your sentence transformer in PyTorch. Bring it in, do it in PyTorch way, the way it's described in the model page. You also get 0.9186, so you haven't lost anything. You can do more checks, but really it's just a smoke test to make sure that when you convert to onX, it's doing what a PyTorch model will do, right? You can also do some benchmarking. You'll see this one runs a little faster. The onX will be like, PyTorch will take a little while in CPU. So there in Teradata, we have a Python library called Teradata ML. And then you can, there's a username and a password. And then you can actually save the model into a table as a blob column. Anybody knows a blob column? Are you all working on vector databases and don't know what a blob column is? So it's a binary large object. So basically you can store text. So you can store like binary values in a table column. And you can do a select star, but you won't get anything from the binary. You can do operations though. Yeah. So you got to load both the artifacts for the model, the Onyx, as well as the tokenizer. You need to have both. And then, so what do you do with this? So you have to do this once. And then, so you can now, let's see. Okay, now I'm going to, Teradata ML also has a notion of data frame in the Python world. And it is kind of like the pandas data frame. So it has very similar operations to pandas. So here I'm saying, hey, create a data frame, virtual data frame for the table Consumer Financial Protection Bureau complaints. And then you can do those data frame operations like ID and text. So I got these two fields. And then I'm also checking my table embedding tokenizers where we loaded the models to see what models are there. It's all there. And then I can actually create a view in anyone know table views. Like, so you can create like join two tables and create a view on top. Then you can use the view as table for select query or share it with someone. So you can create like nested views. So it's a declarative language. So you can absolutely wonderfully stack all of these things, provide governance, like who does what, who should see what column, and especially in banking, it's very important that the PII is not exposed on certain views. And so you have control over how that, it's a data management problem, right? So basically here what we do is that we call a UDF, user-defined function called tokenizer encode. And then we can pass this CFPB complaint. This table is actually distributed on the Teradata amps. It probably has like, I don't know, 100,000, a million rows. And this particular system is not a big, but imagine like a bank, it'll be split 500 ways inside, stored in 500 shards inside with that amount of parallelism sitting on top. That's why when you make some queries in Teradata, it'll be like a blindingly fast because it's done it locally and then it aggregates it. If you're doing an average on a Teradata table, it doesn't go through the full sequential scan. It does average on all the different amps, like MapReduce, right? And it does an average of, it knows how to do the, so every function is a little bit of MapReduce. Even the random forest is done in a MapReduce way. Random forest, so you can do a lot of things. So everything is so fast. And people will be like, wait a second, did it error out? No, we say no, it finished. Well, that's a Teradata story right there. And then you can also pass the tokenizer, and because it's a table, we say, hey, use the by BG small. And then you know all of this, like attention mask, and then it tokenizes it into, and it doesn't quite run it yet because we're creating a view. It's not materialized. It's just set up, like, it's kind of like a late binding, right? So you just create it and it just stays there. And then now you're using the model Onyx scoring on top of the tokenization. And then the output of this is a little bit binary. So we have another function called vector to columns that converts the binary into individual columns, the embedding columns. So when I run this gets invoked, vector to columns on complaint embeddings, and then this runs. And then because it's dependent on this one runs first. So this one runs first, and this one runs first, and this one runs like chained execution, like late execution, right? Like a PySpark pipeline, very similar to the concept. And then it finishes all of that, and then you get text, and then you get the embeddings, and this is distributed. The execution happened parallelly, no data moved across the network. That shard embedding was run, stored in a local, the final table shard. So that way it's taken up, IO, CPU, bam, it comes back like this. So it's parallel execution. And then everything stays in the same place, all the embeddings. And then, so that's how you create the embeddings. So next we'll do some semantic search. So let's, so again, here is the table that we created, the embeddings in the previous notebook. And here are various topics that I want to match my complaint against, like which one the best possible. Like, hey, I want to find complaints, abandoned application, fraud alert. So every product manager will have something they want to look for in the complaints that are today. So you put them all of that, load into Teradata. Again, you tokenize, you create embeddings on these guys as well, right? So you got embeddings on all the prompts. And then Teradata has a function called TD vector distance that also runs in parallel. Everything happens parallelly, right? Think no data movement. Here I'm saying, hey, run this on the complaint embedding store, but on the topic embedding store dimension. Like, so this gets copied on all the nodes, and then use the cosine similarity formula, and then basically like it just creates a final table, semantic search results. And then now I can go through each one of them and find out like what did it match, and then you get the cosine similarity, right? So you say, okay, this particular complaint, I tried to use ATM machine, I tried to withdraw this amount, false matches can't get money out of the ATM with the highest similarity score, right? So this is amazing. This is the multilingual part. If this was in Spanish, you would have totally caught it, or French. Same similarity every time you run it. No different hallucinations. The only hallucination in an embedding model if it gets the context wrong, and it'll get wrong every time. So then you can go fix the model, you can do something. Which means banks love that. They want to know always how much they are right and how much they are wrong, because they need to add numbers correctly. Okay, so yeah, so this is great, and this one runs also parallelly. So it's actually doing, and now you may be asking, hey, how come you're not using HNSW or FICE and things like that? So we are, like vector stores. Anyone familiar with vector stores? You're familiar with vector stores? They are specialized databases for storing vector, like Chroma and Pinecone. They store, and even they store, but they can only store vector embeddings. They can't store other data. But they're very good at storage and retrieval. The retrieval speeds are really fast because they do some sort of a hierarchical way of getting to the embedding. If you're doing semantic search as opposed to doing sequential, doing cosine one by one by one by one, right? They have a way to get to the point, like really quickly to find the ones with the highest similarity. Teradata just launched the vector store recently. So that vector store can coexist with structured data in the database. And you can do semantic search even without even scanning them parallelly, like parallel scanning, not even parallel scanning. So it does both lookup on parallel shards, so it's like blindingly fast, like the benchmarks will be like amazing. So as you know, vector stores are used for RAG quite a bit. Some of our customers are using already, even without the vector store, Teradata for RAG, because you got the embedding models, you can do the search, and it's only just a question of connecting an LLM outside Vantage. We also have some cross-encoder support in the next version. We'll also support BM25. You heard about BM25? Best Match 25. So it's kind of like a very n-gram-based. So now you'll have a combination of embedding search and also n-gram-based best match, like a Solar search or something like that. So you can do both lexical and neural search on the same data before you give it to a RAG pipeline. So yeah, so this is one use case, which is very popular. So one of the things you'll notice is I'm using a lot of SQL within Python. And why are they not Python libraries? It's because a lot of customers are using traditional ATL, like Informatica, Talent, to move data. That all the bank transaction data from ATMs and everything is going through still legacy tools. And because we support SQL, now they can get customer complaints, go through ETLs to load into the data warehouse. Now we have a way to put the SQL as part of the ETL pipeline to generate vector embeddings every night when the data comes in. So the embeddings are stored in a vector store. So the product managers the next day, they'll have the latest updated complaints already ready to go on embedding form, and they can start doing semantic searches on the text. So that is the beauty of writing it in SQL. And if you really want Python, we have the Python wrapper on top of it. So you can always use Python to talk to a Vantage. So you got all of that. Yeah, so as you can see, like we have all these models running. 1 to 2:30, no? Yeah, so even outside Teradata, the vector embeddings can be used for classification, regression. You can do clustering. We saw semantic search and retrieval. So now you have a combination of structured data, old school analytics, not say old school, very popular way of doing analytics on structured data. Like some of them, for example, if you are trying to build a model, like a GLM model or something like that, you can do it inside Teradata too. We do a distributed GLM modeling inside. We have AutoML. But if you don't want that, you want to build a scikit-learn model and you want to combine that with a vector embeddings running in Vantage, then you can build the model in scikit-learn, and then you can export it into a PMML format. There is a code and then you can bring it in. We have a PMML runtime in Vantage, so you can also do the inferencing with both structured and unstructured, right? So yeah, so there's some we have some just benchmarks in a bank that are actually running all these vector embeddings inside the database. I know, like if you look at like a company like Oracle, they also have, or Snowflake, they also have ability to run vector embeddings through semantic search, but a lot of them use like a GPU sidecars to do that. So they have a GPU sidecar, data has to move there, do it and come back. Of course, it will be faster, but if you want to scale at a cost, same cost, on-prem and or in the future, on the regulatory environments, and so this is the alternative. So one of them is doing about 100,000 emails in less than 6 minutes on a finite ARM system, and they're pretty blown away by that. This one is a text summarization. We try to use a 1.5 gigabyte FLAN T5. It finished 30,000 complaints in 1.5 hours. Now you may think that's not much. I put it on a GPU, like it'll go. No, actually, what they do is they try to send it to an LLM to do summarization because they want to have the best summarization possible. So they created a beautiful prompt and say, hey, please summarize this text. Don't use this. Don't use that. Remove the PI. They gave all of that. They were able to get through about 2,500 on a GPU farm in about an hour. Okay, so this is a sequence-to-sequence model, FLAN-T5 model. They're like super fast. Okay, so GPU is like a Ferrari, but it's sitting in the back of the garage. That's what we say. Like you got to get it in the road and just go somewhere. You know, it's like a drive-in. So this is like a drive-in, right? You want a cheese sandwich. You don't want to get on the waiting list. You want to, get the best chef. Of course, your meal will be fantastic, but you're just hungry. You want to go. That's what this is for. So again, text classification. We also support pre-trained text classification, zero shot. Same concept, tokenization, bringing a model, running in parallel. So just to summarize, your vector embeddings, this is your input, this will be like your output, right? Vector, you're generating numeric arrays from table. Oh, you can also do, if you want to do it the Teradata way, let's say you have a big blog post you want to create the sentence embedding on, but your models don't take more than 512 tokens. So you can actually split the blog into multiple sentences or chunks, and then you can run vector embeddings and you can mean pool them, all of them in Vantage, like SQL queries. Some people like it. It's all about scale. Okay, so if you talk about Teradata, they won't talk about like 100,000 rows. It's always like 100 million, 40 million, 200 million, or and some of them say, I don't want daily data, I want to run on 2 years worth of embeddings. That's like a couple of terabytes of data that you want to run vector embeddings on. This is the way to go because it's not expensive. There's no GPUs involved, there's no waiting time. You just run it along with, and Teradata also works on workload management, which means that it knows how to throttle the CPUs in a way that it doesn't stop the other queries from running. So so it doesn't hog 100% CPU, right? These neural models will take 100% CPU. So there's like a lot of things you can do. And then and then you can also do clustering. You should try this even on a Python notebook. You don't even need Teradata. Take some text, run some embeddings, do some k-means clustering, and then put a word cloud on it. You'll be shocked how good the embeddings are able to bring things that are similar to each other. Even it could be French or Spanish or English, they'll all come into the same cluster. And they're talking about the same topic. Most recently, some of our customers are they're saying, I don't want to do text classification with embeddings. I don't want to have labels. I want to have a model and just go and classify whatever I want. Now we are telling them, do text classification using semantic search. Provide these prompts like I showed you, right? Find the highest similarity, and then instead of probability, you have the similarity score. And how do you know it's correct? It's very simple. You have a holdout set, a hand-labeled holdout set, and then you compare the results. If the results are good, then you got yourself a model. Who says it's got to be XGBoost? So you wanna have a way to work well on holdout data, right? Like if you have a holdout set, label set, you want to be able to do actual versus predicted with the highest possible accuracy. Especially with highly imbalanced multi-class problems. Like it's very hard to build a model on highly imbalanced multi-class. Have 10, 20 classes and the data is highly imbalanced. Tell me a good way to do it. Like you can probably use TensorFlow. Neural networks do a great job with multi-class, but you can only get up to so far. The minority class will get chewed up by the majority class always. You're going to find a lot of them misclassified to the majority classes. So this semantic search doesn't care about individual classes. It just goes and matches them. And you can build another model on top of that. So I'm just saying like how useful it is. So you can do RAG, we talk about summarization, pre-trained classification, and this is the one that we're working on. So create embeddings on entity matching. Anybody work with entity matching problems here? So, have you seen the credit card statements where you have the merchant name? Sometimes it's very abbreviated. PayPal would be PYPL star or, so you got all of that. And then there is a big golden dictionary of all the merchants on the right side, and you're trying to match these transactions to the merchants, right? Abbreviations, like I said, sometimes multilingual, very hard to match using traditional technique. If you use something like a Levenstein distance or like a string similarity functions, like Yarrow Winkler or something, it will actually go and look at, like the actual characters or words and then try to match the similarity score and split them up and what's common versus what's different type algorithm. What we found out that if you create embeddings on the ground truth of matching entities, and then you build a classification model on top of that, you can totally now match entities with another 10, 20% higher score than traditional techniques. Not only that, you can also use the traditional technique scores as features for your classification model. So you talk to us and we can show you how we can do it. I don't know, but I didn't want to give you too many details. I know it's a pretty intense workshop. So yeah, and the thing that I was talking about is you can connect a Tableau dashboard, existing SQL dashboards to, you can do semantic search on a database. So if you want to actually play with some of this, we have the URL clearscape.teradata.com. Clearscape is what it's called. You can go sign up for it. And then, or you can go to teradata.com and say try for free and fill up your, your form or whatever. And you have like an instance in the cloud that's available running for I think like up to 45 days or 90 days or something like that. It's got auto shutdown. You can create like a couple of instances. There's no GPUs or anything. It's a small one. But there are if you go to click use cases and check on language models, the notebooks that we talked about, they're all there. You can spin them up and you can just run them and see how, if you're interested. And if you already have Teradata in your company, you'll be able to appreciate that. If not, you can talk to us. And then we'll be able to help you, help you get going on how to do some of these. Yeah, so I think this talk was for an hour and a half, but I think I just want to make sure that we have enough time for questions and we can finish early. I know it's your last day, I guess, so I don't want to keep you here too long. I think I'll also get you some coffee break in the afternoon. So. Because it's a very large room.
Thank Thank you. So thanks for the nice presentation. I missed first few minutes, because maybe that's the reason, but I don't quite catch some part of the presentation. One part is that you talked about the semantic search, and that you don't use HNSW, but it's still fast. But what was the trick? And
Yeah, our vector database does have that, but this is the non-vector database version. The trick is because the data is distributed, the embeddings are distributed fully, right, on multiple, I told you like Teradata's parallelism. It runs on so many CPU cores across so many nodes. So when you create the embeddings are also distributed across all these nodes. So every CPU core will only see that slice of data in the table. It will only work with 100 rows. Each one of them will work with their own 100 rows. But when you count the number of rows, it will look like you're sitting on a big table, but it's really distributed across. So the compute is attached to the storage in some way. Okay, so when you run the cosine similarity, all of them will go through that small slice of data really fast. It's called parallel sequential scan. It's one of the Teradata's way of doing parallelism.
It's an exact search. It's not like...
Yeah, it's an exact search, but because it's a parallel, you have the luxury of abusing the system to do that way, to do it. But what we have done in the next version of Vector Store is we have also implemented HS and NW on top of that. So even that little sequential scan will also be eliminated, and you'll get like a tree search, right? It'll get to the centroid and then find the small world algorithm.
Yeah, now it makes sense. Thank you.
Other questions? Oh. For the record.
Thank you so much for the presentation. It was very interesting that you didn't run into hallucination. I'm curious to know why this happened and how did you manage that?
Yeah, these small models typically it's very simple models, which means there's no randomness in it. It's just the way it's built in. It is not supposed to be creative, so there's no temperature setting or anything like that. And the seed is also locked in pretty much. If you change the seed, then your sequence to sequence will be separate. But the way we are doing it right now is that we lock the seed inside. So it's very easy to manage, even outside Teradata. And then it is just like a simple decoder. There's no random seed to start with, or even, so that's how they're built in the first place. That's been our experience. Whereas LLMs will have a lot more randomness inside. It has to, the way it's done, right? Yeah, everything has its own application, but you want to use the right tool for the right job, for the right application. And
why there's no hallucination?
yeah, because the models, the seeds are pretty much set inside. There is no randomness inside.
Okay, you fix the seed.
Yeah, the seed is fixed, and it's much more, even if you don't fix the seed, even if you use the fixed seed inside, or if you specify, then you're always going to get, just like a regular machine learning model, same input, same output. If you don't like it, fine tune it and evaluate it. And once you evaluate and put it in production, no surprises. You'll know what will go right, you'll know what will go wrong, right? And it's measurable, so it can be deployable. Right? Imagine going to a model risk office and say that today the person will get a loan, but tomorrow, I don't know, depending on what LLM had coffee in the morning or not, right? So this is why it's extremely important. Well, LLMs are very creative and it's great, okay? You can answer a lot of questions, but putting in production is a completely different story, because now it's become a life or death decision. Imagine if your LLM is making medical decisions for you. Today, I think maybe you should operate your eye, and I don't know, you want to be very clear, yes or no, right? You want to be very clear. Or you're wrong, right? You say, okay, then go fix it, right? So you have this feedback loop wherein even the embedding models are not always correct, right? In the sense, it can give the same embeddings, but it can be semantically picking up wrong things and create the embeddings in the wrong space of the embedding space. But at least you can evaluate it and say that it's not really doing good with health topics, but it's doing good with finance topics. Maybe we should fine tune it. Maybe we should put some guardrails. So then you can fine tune it, evaluate it, like a RAG evaluation type things, right? So you evaluate these things. So yeah, that's why the small models are great. Like I wouldn't say so much about small LLMs because small LLMs still has a little bit of randomness to it. I'm talking about language models. That's why it's called language model specifically. Embedding model, sequence model, very manageable. Forget about Teradata, just outside, even outside, even on a GPU farm. You can just make sure you pick the right model for the right task. You know. Anything else from anyone?
Thank you for your talk. Can you clarify or at least talk about the decision on the threshold for finding the positive matching either in the embedding and the text entity? Because you're going to have like a numerical number for the co-similarity, right?
The embeddings.
Yeah.
Oh, so you want to know like what?
What is your thumb rule for saying, no, this is a exact match or not?
I
right?
see.
Because to avoid false positives.
Absolutely. I will show you. Let me explain, okay? I gotta show you this. I gotta show you guys this, and then I will talk about the 1 second. Okay, I didn't quite want to show you this. This is from a video gaming Twitter notebook. Some profanity here, the middle schooler language. I can tell you that this is like the worst English you can think of. Swear to God, I don't know if you have any middle school nephews or whatever. It's like, yeah, it's like because the video game, they have a different lingual English. They can't even complete sentences sometimes, I think. Okay, I shouldn't say anything wrong about video gamers. Video gamers, forgive me. And I was actually doing a semantic search here, right? I was saying, hey, tell me positive and upbeat comment on the Twitter feed, and negative or abusive comment, and video game crashes every now and here, display problems with software. It goes and finds this with graphics go too freaking crazy with 0.71 similarity. Okay. So now we have a very interesting multi-class problem, right? So first of all, when you do semantic search, it's one thing to search on one topic, and then the other thing to search on 5 topics to see which one matches the best. Usually it's never, unless you're a Tableau, like a product manager or something, you're generally going to trying to classify them into 15 different categories. It's a common I've seen. So let's just talk about the simple case first. You're looking for one thing and you're finding the thing yes or no, right? So this comes from one thing that I've seen is if you really want to have control over the threshold and false positives and negatives and confusion matrix, you do need to have a ground truth set on what is positive and what is negative. Okay, so what I mean by that is you need to handcraft these into what would be considered a positive comment versus what is not a positive comment for a binary classification use case. And then you can do a semantic search and come up with a predicted text, and then you're going to have a range of things, and then you'll be able to see to some extent how that matches with the binary classifying. So let me see if I can explain that just a little bit. So this is what we are telling our customers, like you pick a threshold. Let's say you pick a threshold 0.68 or something, just like a confusion matrix, right? Confusion matrix, you do have to specify a threshold. Usually it's F1 score. So here you pick some threshold, and then you look at your predicted actual versus predicted. So this, and then treat everything as 1 above the threshold, everything as 0, and then you have the handcrafted 1 zeros, and then you have the actual versus predicted, right? And then you do a confusion matrix, and then you can find out whether that's the one that you're looking for. So you do have to play with the threshold manually to some extent. But you need to have the ground truth. You need to have it side by side, but that's how you're going to get the confusion matrix, actual versus predicted, right? All we're doing is predicting based on the prediction will be similar to similarity. The threshold will be like some, so you can do like every decile, like 0.1, 0.2, 0.3, 0.4, and you can look at that, and then you can even do like gains and lifts based on that. So there is a way to do this. That's, end of the day, it's just a model. It doesn't have to be an XGBoost model. You just need a threshold, and you know the confusion matrix, and so you got yourself a model. It doesn't have to go through the whole random forest thing, you know.
Just a technical question in that. If you introduce ground truth cases, should you fine-tune the model before proceeding if you know you're going to be using ground truth cases beforehand?
Yeah, no, it's a great question. Here, you'll notice one thing in semantic search, there's no hyperparameters. All you have is the prompts. So you have full control over changing these prompts and seeing if you're getting a better result. Sometimes it's a semantic match, right? Maybe you're not saying it correctly. Maybe you have to say it a little bit differently. So there is a little bit of art and science, but there is a way to measure. Because you have the ground truth, you can always go back to the similarity, have it. And this is one lever you have. The other lever is switching the model, trying a different model. So you can change the model, you can change the prompts, but there's no auto ML of anything to do this. You got to do it by hand and try it out. But the good news is, the really good news is, what I find exciting coming from my AI company I used to work with, is that it's a multi-class. You can get amazing macro F1 on a multi-class classification problem, imbalanced data classification problem. There's no way you're going to get it from any algorithm. Really good false positive and negative ratio across every individual class, because usually when you train, the data is usually imbalanced, right? You'll get a fewer examples of one class and usually more. Then you do imbalance sampling, you're going to hit and miss a lot of things. But here, even though there is one row that matches this, this one, let's say there's only one row that matches this issue, you're going to get it. You're not going to miss it and get misclassified, as long as you have the threshold figured out. Yeah, so I hope I answered your question. Kind of? Yeah, so all I'm saying is you still need the ground truth. You have two things. You have the threshold to play with, you have the prompts to play with to match actual versus predicted, right? And then you have the model to play with. So those are the three things. But you can still get the confusion. You can still get the scores. The actual versus positives, false positives and false negatives. That's how you know that your prompts are working correctly and the model you have chosen working correctly and your threshold is correct. So, because at the end of the day, after you find the correct threshold and you have a good sense of false positives and negatives, then you can use the same threshold in production, right? Because when a new data comes in and you're doing a semantic similarity across all of these prompts, then you can use the threshold to say that, about this, for every class, like above this, that I'm actually getting true or false, or whether it belongs to the category or not.
All right, how about that side of the room? Anybody questions on that side of the room? No? Nothing? All perfectly clear.
I know I didn't answer your question, Fly. I may missed something, but I will come back to it. Maybe I didn't get it.
All right, well,
Right.
anything else you want to, Karthik, should we wrap up? Or?
Yeah, I think so. I think they've been very patient for an hour and a half, I think. Get some coffee going. Thank you so much for coming today, and